Okay, so here in these examples, we're going to do applications of Extrema. So suppose we're given the information about an object being thrown vertically upward, and its position at time t is s at t, which is 100 plus 64t minus 16t squared. Time is greater than or equal to 0 and is measured in seconds, and its height, s at t, is measured in meters. And we want to find the maximum height of this object. So if you think back before, when we were given a function, f at x had equaled something, and we wanted to find the absolute maximum or minimum, what we did was we took its derivative and we obtained the critical numbers by setting the derivative equal to 0 or a d&e, and the biggest y was the maximum and the smallest was the minimum. Or we also saw that by a number line test where f prime had only changed signs from a positive to a negative at a particular number, say 2, then that would mean we would have a maximum at x equals 2. That's not the maximum value, but that's where the maximum the value would occur at, would be at x equals 2. So it's very similar to that, but now this function has meaning. It's the height of an object being thrown vertically upward. So to find its maximum height, we want to maximize this function, s at t, which would entail taking its derivative. So s prime at t would be equal to 64 minus 32t equals 0. Set that equal to 0 and solve. And we learn that t equals 2. Now we don't know that in 2 seconds would this be the maximum height. Is this when the object would reach its maximum height? So let's take a look at a number line test. The critical number is only 2. Time is at least 0. And this is s prime. So if we pick 1 as a number to test, we would get a positive. And if we pick 3 into here, we would get back a negative. Since s prime only changes sign from positive to negative at t equals 2, then this confirms we have a maximum at t equals 2. So therefore, there is a max at t equals 2 seconds. To find the object's height at that particular time t, just substitute 2 back into the original. So s at 2 would be equal to 100 plus 64 times 2 minus 16 times 2 squared. And in grinding out the arithmetic, we would get 164 feet. This would confirm now that the maximum height is 164 feet using the first derivative test. However, we could have also had used the second derivative test. S double prime at t is negative 32, and s double prime at 2, we take the critical number from the first derivative, put it into the second derivative, and this yields a negative 32, which is less than 0. So then therefore, by the second derivative test, since s prime at 2 equals 0 and s double prime at 2 is less than 0, then we know that there is a maximum at t equals 2 seconds. And then again, by substituting back into the original, we would get 164 feet, because this is when the object achieves its maximum height. Before, we solved the same problem where we didn't involve the number line test. We just know that the derivative of position is velocity, and we observed that when the velocity was equal to 0, that is when the object would have reached its maximum height. So we did this earlier, but setting v equal to 0 and solving. Here, we're using the first derivative and second derivative test to confirm where we have a maximum. Okay, another example involves maximizing an area. Here we maximized a position function. Now we're going to maximize an area. So in this example, suppose we are given 1,000 feet of fencing. And with this fencing, we have a building or a garage bordered, and the other three sides will be the fencing. So we're going to use some fencing to enclose a rectangular piece, maybe perhaps a garden. And on this side is maybe a building of some sort, acting as a border for the other side. And we are given 1,000 feet of fencing. So the question is, what dimensions would yield a maximum area? How long this way do we go and this way do we go to get the biggest area with 1,000 feet of fencing? So let's call this y and y, since those sides are equal, and we'll call this x. So then the area of this rectangular piece is x times y. This is what we want to maximize. We want to maximize that area, which means we would have to take this derivative, set it equal to 0, and find when we have a maximum. Okay, well, we preferred, if we could, to take this derivative in terms of one variable. So if we look back here, we can realize that the sum of these sides, x plus 2y, would be equal to 1,000, the perimeter of the rectangular piece. And solving this easily for x or y, we would get x equals 1,000 minus 2y. We can now take this and substitute this back and have 1,000 minus 2y times y. This is x. And now I just have a function of y. I can distribute. So a of y equals 1,000 y minus 2y squared. This is what I want to maximize. Now that it's in terms of one variable, I can just easily go ahead and take its derivative. So a prime at y would be equal to 1,000 minus 4y. Set it equal to 0. Negative 4y would be equal to negative 1,000. Divide, and y would be equal to 250. Okay, so then now by a number line test, we'd have 250 and 0. And we could see here that the domain would have to be up to 500. Anything beyond that would yield a negative dimension, which would not make sense. So this here is a prime. Even if you did not realize that, you'd get away with confirming that you would have a maximum at 250. So if we pick, say, 100, substitute it into the first derivative, we'd get a positive. And if you were to pick, say, 300, substitute it into the first derivative, you would have a negative. So since a prime only changes sign from positive to negative at 250, this confirms we have a maximum at y equals 250. Again, we could have done the second derivative test, had taken a double prime at y, and that equals negative 4, and a double prime at 250 is equal to negative 4, which is less than 0. So then by the second derivative test, since a prime at 250 equals 0 and a double prime at 250 is less than 0, then by the second derivative test, we would have a maximum at 250. So if y is 250, what's the other dimension? Well, x equals 1,000 minus 2 times 250. X would be 1,000 minus 500. X would be equal to 500 feet. So these would be the dimensions that would yield a maximum area. And that would be 500 feet by 200 feet. And if we wanted the maximum area, then we would just multiply the two to get the maximum area. Okay, so once again, we were given 1,000 feet of fencing. We were to form a rectangular garden, perhaps, where one side is a building or the back of a garage, and we wanted to enclose these three sides using 1,000 feet of fencing. And we took the equation that we wanted to maximize, x times y, eventually had taken its derivative, and verified that a max was at y equals 250. Okay, so back here again, it's easier sometimes to solve for one variable in terms of another and do the substitution so that we don't have to do a product rule on two different variables. We could do that, it just is a little longer to get there. And realize this is the function we want to maximize. We wanted to maximize the area, so that is the function we take the derivative of, the function we wanted to maximize. Okay, next, and the last one will be maximizing volume. So suppose we are given a rectangular sheet of metal, and this sheet of metal is 16 inches by 21 inches, or even a piece of cardboard, which is very similar to a piece of paper. And what we want to do is to take this piece, 21 by 16, we want to form a rectangular box out of this piece of metal or cardboard. And the box will be formed by cutting up the ends somewhere and folding them up. So it's just like being given this piece of paper, and we want to know where would we cut along the edge here so that when we fold it up, such as this, we would start to get the biggest volume of a rectangular box. So what dimensions would yield the biggest volume? So since we don't know where to cut up along these sides, we'll call them x. And of course it's the same around all sides. So now we could say that this side has a dimension 16 minus 2x, because that's what we're removing from these two corners, and what's left is 16 minus 2x. And then over here, since we're removing x and x, what's left over here is 21 minus 2x. What we want to maximize is the volume of a rectangular prism, which is length times width times height. The height is x. That's what we're cutting out from each corner, and we fold it up. That's the height of the rectangular box. So let's take a look at putting it all together. As a rewrite, we would just have x times 21 minus 2x times 16 minus 2x. And now this is what we want to maximize. So we want to take its derivative. A couple of different things we could do. We could do a product rule there, actually, or distribute and clean it up. So let's do the more common approach, which would be to FOIL and then distribute. So we would have here x times 336 minus 32x minus 42x plus 4x squared. And then in cleaning that up, we would have x times 336 minus 74x plus 4x squared. And then distribute the x through, we'd get 336x minus 74x squared plus 4x cubed. So again, we didn't take any derivative yet. All we just did was get our volume formula, look at the picture, substitute our dimensions in terms of x, FOILed, clean it up, and then distribute the x through. Now we'll take the derivative. That v prime is equal to 336 minus 128x plus 12x squared. So v prime is equal to 12x squared minus 128x plus 336. What we can factor out from there is a 2, and we would have 2 times 6x squared minus 74x plus 84 equals 0. We can actually factor this into 3x minus 28 times x minus 3. So now the factors equal 0 when either x is 28 thirds or x is equal to 3. Now here we have 2 critical numbers. Which of them will yield a maximum? Well, if you look here, this is 9 1/3. If you were to try and substitute 9 1/3 back into here, you would end up with a negative dimension. So this is out of the domain of the function. So then we would go from 0 to 8. You could see here that beyond 8 we would have a negative dimension. So our domain would be from 0 to 8. This is v prime, and our critical number is 3. If we test in 1 back into here, we'd get a negative times a negative, which is a positive. If we were to take, say, 5 and substitute it back into here, we would get a negative times a positive, which is a negative. Since v prime only changes sign from positive to negative at x equals 3, then we would have our maximum at x equals 3. Now what is x? X is the height, which meant then folding up that piece of cardboard or metal 3 inches from each corner would give us the biggest volume. So if you were to take this and substitute it back into each of these, you'd get the dimensions would end up being 3 by 10 by 15 inches. These are the dimensions that would give us the biggest volume of a rectangular box. So once again, we were given a sheet of cardboard or a metal 16 inches by 21 inches. And the question is, where do we cut along the corners so that we fold them up, we form a rectangular prism of the biggest volume, having the biggest volume. So then when we remove these 2 corners, we're left with 16 minus 2x. When we had removed these 2, we're left with 21 minus 2x. And then by substitution, we end up with our volume function in terms of x, and this is what we want to maximize. And then we just FOILed, distributed, taken its derivative, set the derivative equal to 0, and verify that at x equals 3 we have a maximum. And of course we could have used the second derivative. We could have gone on to say that v double prime equals 24x minus 128, and v double prime at 3, because it's our only critical number right here, is less than 0. So then by the second derivative test, we would also have a maximum at x equals 3. So either by the first derivative test, we verified it, or by the second derivative test. But it does need to be verified, because in some cases coming up in the future, the absolute maximum or minimum may not be at a critical number as it has been. It could also be at the endpoints. So we cannot assume that the maximum always occurs at the critical number. The absolute extrema, remember, can occur at a critical number or at an endpoint yet. So therefore, we need to make sure that we do the number line test on the first derivative and verify that in this case it changes sign from only positive to negative, or by using the second derivative test with our only valid critical number because the other one was out of domain.